Hi. So in this section, we will still talk about the concavity test. So what is this concavity test? Well, um, if the second derivative is negative on a given interval, like in this case from A to C, the second derivative is negative on this interval. So if since the second derivative is negative on this interval, what can we say about the graph of this function? So the graph of the function is concave downward on A, comma C. From C to B, the second derivative of the function f is positive. In terms of the function is concave upward on CB. So CU stands for concave upward. CD stands for concave downward. Now, wherever there is a change of concavity, whether it's from CD to CU or CU to CD at a given point, so that means at that point the second derivative is 0. Like at this point, which is a C, there's a change of concavity. So this graph is going from concave down to concave up at this point C. So that point C is called point of inflection. That's where the second derivative is 0. Okay, so now we go by using an example. So they give us this function f of x equals x to the fourth minus 4x cubed. So the first question is to find the critical point of f. We know when we discuss the critical point, we already did it in the past. All you have to do is take the first derivative and then set the first derivative function to be 0 and then solve for x. So when you take the first derivative, we get 4x cubed minus 12x squared. We set it equals 0 and then we solve for x. So after setting this equals 0, we have a common factor, which is 4. We can divide by 4. So we get x cubed minus 3x squared equals 0. When you look at these two terms, there's x squared, this is a common factor. So do not divide by x squared, because x squared is a variable. You don't divide by a variable. You factor out a variable. So we factor out x squared. We get x squared times quantity x minus 3. Set x squared equals 0. You get x equals 0. X minus 3 to 0 gives you x equals 3. So we have two critical points. We have a 0 and 3. Second question, find where the function is increasing and decreasing, and then find the local maximum and local minimum value. Okay, so first we have to plot these the critical points on the number line. So we have a 0 and 3. We plot them. Okay, and then we say that so on the top row, we put f prime of x. At the bottom row, we put the function f of x. So this is like a table. So we have two critical points. The two critical points will divide the number line into 3 sub-intervals. So here, on the first interval, we pick a test point, like -1. We're going to plug this into the first derivative function. Okay. If you plug in -1 here for x, so it's always in f prime, okay, of x. So you plug in -1 for x, you're going to get a negative number. So that means the first derivative is negative on this interval. In terms of the function, it means the function is decreasing on that interval. If you pick x equals 1 on the second interval, as a test point, you plug this into here, you're going to get 4 minus 12, which is again negative. So the first derivative is still negative again. So that means the function is decreasing on this interval. And then we pick a number 5 for x into the first interval to give you a positive number. So that means the the function is increasing on this interval from 3 to infinity. So we say f is increasing on bracketed 3 comma infinity, and then it's decreasing on negative infinity up to 3. Okay, based on the first the first derivative test, because the function the first derivative is changing sign from negative to positive at x equals 3, that make f of 3 to be a local minimum value. So we know at x equals 3 there is a local minimum, and that local minimum value is f of 3. So you have to go back to the original function and evaluate it at x equals 3. So that gives us negative 27, which is the local minimum value. Next, we go to number 4. Find where the function is concave up and then concave down. Anytime you hear concavity, concave up, concave down, remember you have to move to the second derivative of the function. Okay, so you have to take the second derivative of the function f of x. Concavity implies second derivative. Point of inflection implies second derivative. So we first, this is the original function, this is the first derivative, and then we take the second derivative, we get 12x squared minus 24x. Set the first derivative equals, the second derivative equals 0, so, and then solve for x. So we have 12x squared minus 24x equals 0. We can divide this equation by a number 12. It gives us x squared minus 2x. We can factor out x. You get x times quantity x minus 2. We set x equals 0, and then we set x minus 2 equals 0. We get x equals 0, and then x equals 2. So what do we do with this number? This is where the second derivative is 0. The second derivative is 0 when x is 0, also when x is 2. So our next step is to go plot those numbers 0 and 2 on a number line. Okay, so we have a x equals 0 and a x equals 2. On the top row we put the second derivative. This time it's the second derivative, and the bottom is still the function. The bottom row is still the function. So because we have a 2 zeros of the second derivative, the 2 0 will partition the number line into 3 sub-intervals. This is the first one, that's the second interval, and that's the third. So what we have to do is pick a test point on every interval and then evaluate the second derivative at those test points. So what is the second derivative? The second derivative function is basically this function here. Okay, that's the second derivative. So if you pick, for example, -1 on this interval, you go to the second derivative function, you plug in -1 for x, it's going to give you positive 12, and then a plus 24. So you're going to get a positive number. So that means the second derivative is positive on this interval. What is it by the concavity test? What does it mean? It means on this interval, the function is concave up. So we either write it as big U here, or we use a CU to represent concave upward. Then you go to the second interval, you pick a number 1, for example, into the function. The second derivative function, it gives you, so you get like 12 minus 24, which is negative. So we know the second derivative is negative here on this interval 0 and 2. So we say by the second derivative, the concavity test, we say that the function is concave downward on 0 to 2. And then when you pick up 5 for x into the second derivative function, it gives you a positive number. So that means the function f of x is concave upward on the interval 2 to infinity. So we can make the statement based on table that f is concave upward on, so we have concave upward here and there. So it's concave upward from negative infinity to 0, union 0 to infinity, because we have two places where the function is concave upward. and the function is concave downward on 0, comma 2, this interval. Now let's look at the change of concavity. So here we have the function is, the second derivative is changing sign from positive to negative at this number x equals 0. Okay. Or we can say the function is going from concave upward to concave downward at this number x equals 0. So that make x equals 0 a point of inflection. Similarly, there is a change of second derivative sign from negative to positive at x equals 2. So that makes x equals 2 as a point of inflection. You can also argue using concavity. We're going from concave down to concave up at x equals 2. That makes x equals 2 a point of inflection. So we have a 2 points of inflection, x equals 0 and x equals 2. Thank you.